Hey everyone, and welcome to the AI Research Roundup. I am Alex. Today, we're looking at this post from Google Research, dated May 23, 2025, Fine-Tuning LLMs with User-Level Differential Privacy. It's all about enhancing LLMs with private data using differential privacy, or DP. That's a technique ensuring privacy during model training, often by adding noise. This research specifically tackles user-level differential privacy, a stronger guarantee protecting a whole user's data, not just individual examples. The authors optimized two key data sampling strategies for this: example-level sampling, or ELS, which selects random data examples, and user-level sampling, or ULS, which selects random users. They found that for example-level sampling, less noise is needed than previously thought. Moreover, user-level sampling generally performed better. Overall, they show fine-tuning LLMs with robust user-level privacy is practical and boosts model performance. Alright, to help visualize this stronger user-level differential privacy guarantee, this diagram presents two scenarios. In the first, we see a dataset containing data from multiple users. For instance, user 1 contributes several triangle-shaped data items, user 2 contributes circles, and user 3, a diamond. This dataset then undergoes noisy training. That's the part where randomness is introduced to protect privacy to create a model. Now in the second scenario, all of user 1's triangle data is completely removed. Yet after this altered dataset also goes through noisy training, the resulting model looks the same. This really highlights the core idea. It's impossible to determine if an entire user's data was part of the training or not. Okay, so the article then provides a visual to help understand the basic training process they build upon. This figure shows, on the left, a collection of data examples represented as colored squares labeled X1 through X9. This data then notionally feeds into what's labeled SGD, which stands for Stochastic Gradient Descent. That's a common algorithm for training models where data is processed in small batches to compute updates called gradients. The diagram then indicates this process transitioning into DPSGD, or Differential Privacy Stochastic Gradient Descent. This Differential Privacy Stochastic Gradient Descent is the key modification where random noise is added to those gradients, protecting the privacy of the training data. Alright, so before we even get to the sampling strategies within Differential Privacy Stochastic Gradient Descent, there's a crucial pre-processing step. This figure here shows it clearly. On the left, you have an original data set with various users. User 1, User 2, etc., each providing a different number of data examples. Then, on the right, it's after contribution bounding. This contribution bound, which is the maximum number of examples a user can contribute, is set to 3 in this illustration. So, user 1, who initially had 5 examples, is now limited to 3, while user 4, with 2 examples, remains unchanged. This step is vital for both of the sampling approaches. So, after that contribution bounding step, this figure gives us a nice visual comparison of the two core sampling methods they explore. On the left, we have example-level sampling. You can see data examples, X1, X2, X3 from user 1, and so on for 4 users. The idea here is that individual examples are picked, potentially across different users, to form a training batch. Then, on the right, it's user-level sampling. Same data, but now the approach is to select entire users first, and then all their examples, up to that contribution bound we just talked about, go into the batch. This difference in batch creation is key. Okay, moving to the results. These plots compare example-level sampling, the blue line, and user-level sampling, the orange line, against a none baseline, which means no fine-tuning. The vertical axis shows loss, a measure of model error, so lower is better. The horizontal axis is the privacy level epsilon, or epsilon, a key differential privacy parameter, where smaller values mean stronger privacy. We see across 3 different compute budgets that user-level sampling generally results in lower loss, indicating better performance, especially with more compute. Crucially, both privacy methods outperform the baseline. Okay, so before those direct performance comparisons we just saw, the authors first had to optimize example-level sampling. These 3 plots here illustrate a critical improvement they made. Each chart represents a different noise multiplier, which essentially controls how much randomness is injected for privacy. On the horizontal axis, we have the contribution bound, and on the vertical, epsilon, that privacy level where lower is better. The key thing is the blue line, their MOG method, which stands for Moments Accountant, a sophisticated way to precisely track cumulative privacy loss. It shows epsilon growing much more slowly, almost linearly, with the contribution bound. Previous black box calculations, shown by the orange line, suggested epsilon would grow exponentially, meaning privacy guarantees would degrade much faster. This new analysis is a big deal for making example-level sampling more practical. So, looking closer at these results, especially in the leftmost plot representing the smallest compute budget, we see that for very strong privacy levels, that's low epsilon, example-level sampling can perform comparably to, or even slightly better than, user-level sampling. However, as the compute budget increases, shown in the middle and right plots, user-level sampling consistently achieves lower loss, meaning better model performance, across various privacy settings. This reinforces that both methods, especially with the optimizations discussed earlier, are a significant improvement over not fine-tuning at all, which is that flat green line way up at the top. Alright, so to wrap things up on this insightful work, it's clear that fine-tuning LLMs with user-level differential privacy is not just possible, but also beneficial when done right. The researchers showed that user-level sampling generally performs better, especially with more compute, though example-level sampling, particularly with their improved noise analysis, can be very effective in high-privacy, low-compute scenarios. These optimizations, including better ways to set the contribution bound, make a real difference. Ultimately, this research enables model trainers to adapt LLMs to sensitive datasets while providing strong privacy protections for users. That's all for this AI Research Roundup. Thanks for tuning in.